Thanks for watching, and today I want to show you a very beautiful formula related to Laplace's equation, namely the mean value formula. And if you love multivariable calculus, you're in for a treat, because this is very, very intense multivariable calculus. So here's the theorem I want to show today. So suppose you have a solution of Laplace's equation. So suppose Laplacian of u equals to 0. And that's just the same as saying if you take ux1 x1 plus ux2 x2 plus dot 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 plus uxn xn. Suppose u satisfies this. Then for any r and any s, any r and any x, you have the following. Suppose you have the sphere radius x. So this is x, and this is a radius r. And let's denote this boundary to be the boundary of bxr. In other words, the sphere radius r. And suppose you have a value here, u of y. Or suppose, I guess, you have a point. And moreover, suppose you calculate the average value of u on that sphere, which I denote by this. Average integral of b of xr, u of y, and because we're on the surface, we have to use this surface measure, so ds of y. This weird term is just another way of saying the average value of u on that sphere. Turns out the average value is exactly the value of u at the center of that sphere. How cool is that? So literally we literally found a function whose value at the center is equal to the average value of that sphere. And it turns out there was nothing special about that sphere. You can do the same thing about that ball. So the ball itself, we denote it by bxr. If you take the average value of u on that ball, you also get the value of u at x. Really neat, in my opinion. So it's a function that equals to its average value. And I think what's also nice about this, it shows you that solutions of Laplace's equation are pretty smooth. Because suppose you had a function, again, suppose this is, bxr, and you have a function which has a spike here. Okay? And this is sort of u. Well, this function, it cannot solve Laplace's equation, because by what I said, suppose, again, this is x, and this is u of x. Well, the value of u at the center is much bigger than the average value on the boundary, because the average value here is just a very small value, but ux is a huge value. And it also illustrates a bit the concept of the maximum principle, which says the maximum and the minimum value, they can never be attained inside the region. They have to be attained on the boundary of the region. Which explains if you touch a hot plate, don't touch it at the boundary because it's usually where it's hottest. So, all right, great. And now let me show this, and it has to do with some very beautiful multivariable calculus. Okay, so I guess step one. Again, fix x. X is not important. It's the r that's very important. And define the following function. Let phi of r equal to the average value here over the sphere. And we'll deal with the ball later. So turns out the ball is then much easier once we do the sphere. Okay. All right, and remember we want to show that this equals to u of x. In particular, notice u of x doesn't depend on r, it's constant. So really what we want to show is that phi doesn't depend on r. In other words, show that phi prime of r equals to 0. So first we want to show that phi is constant, and then you'll see it follows that phi is equal to u of x. All right, and now, in other words, what we want to do, we want to differentiate this with respect to r. So let's calculate phi of r. First of all, what is this average integral? Just like in calculus, the average value of a function is the integral of the function divided by the area, if you want, of this object. So by definition, phi of r is uy ds of y of integrated over that sphere divided by divided by that surface area of that sphere. And I've already calculated the surface area of a sphere in a previous video, but the only thing that's very important is that it's the derivative of the of the volume of a ball. And remember, the volume of the ball is a constant times r to the n. So the derivative is n r to the n minus 1 times some constant. It turns out that constant is just the volume of the unit ball. And we call this alpha n. So if you want, this is just the volume of B0. And you have this. Dot, dot, dot. Again, this value doesn't matter that much, but what's important is that it scales like r to the n minus 1. Just like this sphere in R3, it's 4 pi r squared, which is one dimension less than R3. So in this case, x is in Rn, so we have r to the n minus 1. And here's the important thing. We would like to differentiate this with respect to r, but the problem is our domain of integration also depends on r. And this is a big no-no. In theory, you could differentiate this thing, but let's not make our lives too complicated. Let's try to write this in the form that our domain of integration doesn't depend on r. And for this, let's just use a change of variables. So, in other words, we kind of want to write y as x plus rz, because this is centered at x and of radius r. In other words, let z be the following variable, y minus x over r. And what's nice about this change of variables is that you started with the ball of radius x, of centered at x and radius r. Well, because you do minus x, your new ball will be centered at 0. And because you divide it by r, this new ball will have radius 1. So this will in fact be the unit sphere, or unit ball. And well, to do this, we also have to use a Jacobian. So I'm not going to go through this in detail, but in single variable calculus, you have dz is, again, this is constant, so dy over r, so 1 over r dy. But because the sphere is an n minus 1 dimensional object, you have to do it power to the n minus 1. And that's because if you do the Jacobian in n minus 1 variables, you get basically 1 over r, etc., 1 over r n times, n minus 1 times. So if you take the determinant, you get the product of those factors n minus 1 times, and you're just left with 1 over r to the n minus 1 dy. Okay, so in the end, we get dy over r to the n minus 1. And so our original thing is sorry, I meant to say not dz, but like on the sphere, so ds of z and ds of y. So basically dy, but on the sphere, so ds of y becomes r to the n minus 1 ds of z. It's good because what does that tell us? It tells us that this new integral then just becomes the following. So this top just becomes, again, the integral over a new object, which now is the unit sphere. U of y, which is x plus rz, and our Jacobian, which is r to the n minus 1, ds of z. And this is very good because it turns out it makes our job even easier because this r to the n minus 1 comes out. So we have an r to the n minus 1 here. And this precisely cancels out with this r to the n minus 1. So in fact, using this change of variables, we actually have an easier expression. In other words, what did we try to calculate? Phi of r then becomes the integral over the unit sphere of u of x plus rz ds of z divided by stuff that doesn't depend on r anymore, namely n alpha n. Now that is much more easier to differentiate than the other one. So, and now, well, let's differentiate this junk. So, phi prime of r is the derivative of this. And now, the only thing that depends on r is this thing, and assume we can differentiate under the integral. Strictly speaking, you have to use a dominated convergence theorem and difference quotients, but this is not why we're here today. So the derivative of u of x plus rz prime over n alpha n. And now to differentiate u, and again prime just means d over dr. Just use the Chen-Lu a bunch of times. And so this is integral, surface integral over the unit sphere of, if you want u, what variables did I use? Let me see. Yeah, ux1 times derivative of this with respect to r, which is the first variable, z1 plus ux2, z2 plus dot 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 plus uxn, zn, ds of z over n alpha n. And interestingly, we can actually write this in terms of a gradient. So that's the surface integral over the unit sphere of du, and again du of our original variables, x plus rz dotted with z, and again ds of z over n alpha n. Right? All this is good. And now, once we had our differentiation, it would be nice to go back to our original variables. So now, let's just use again another u substitution. So now let y be x plus rz, then ds of y. Again, by the same Jacobian trick, it becomes r ds of z. But because we're dealing with this n minus 1 dimensional object, we have to do this n minus 1 times. So we get another factor of, so not only that, ds of y is r to the n minus 1 ds of z, and we want ds of z. So it becomes 1 over r to the n minus 1 ds of y. And moreover, what happens to the unit sphere once you apply this change of variables? Well, first, the radius becomes r, and you shift it by x units, so you get our original sphere back. So what you're left with is the following. Like, I know, I'm going through years of multivariable calculus with this, so phi prime of r is, again, integral over our original sphere of duy dotted with, so if y is x plus rz, that means rz is y minus x, so z is y minus x over r. So du of y dotted with y minus x over r. And again, we have our thing here, 1 over r to the n ds of y divided by n alpha n. Okay, almost done, at least with this first step. And you'll see, by the way, so far we haven't used the fact that u solves Laplace's equation. So far everything works for any u, and at some point we want to use the fact that u solves Laplace's equation. But first of all, this 1 over r to the n minus 1 is just a constant, so it comes out here. And now let's talk a little bit more about this term here. So how does this relate to our usual sphere? So we have x, and this is our radius r, and we have y, which is on the sphere. And now notice, so if this is x, y minus x is this arrow here, and moreover, if you scale it, it turns out y minus x over r is precisely a unit vector that points perpendicularly to the sphere. So if you'd like, if this is the sphere of radius x and comma r, then this vector here, y minus x over r, that's the unit normal vector to that sphere. Vector to our sphere at y. Well, normal because it's perpendicular to that sphere, and moreover unit because the length is 1, because the length of y minus x is r, and you're precisely dividing by r. So let me write this in more suggestive notation. It's bxr duy dotted with, I think calculus books call this n, and then ds of y over r to the n minus 1 and alpha n. Okay, and some people know what I'm getting at, but we have a normal vector, we have a surface integral, so maybe we would like to use one of our famous, surface integral theorems. And for this, well, let me just state it. In general, we want to use the divergence theorem, which says that the divergence of a vector field, let's see, if you have some domain D, and you take the divergence of a vector field, that's the same thing as the surface integral over the surface of D of f dotted with the normal vector. So, taking this back, we get, this is like our f, and this is our normal vector. So, by the divergence theorem, this equals to the integral over the whole ball of the divergence of du of y, dy, divided by this constant, doesn't actually matter here. And now I'd like to remind you of one more thing. What is the divergence of a gradient? And no, it is not 0. So divergence of du, that is the divergence of the vector ux1 up to uxn. And remember how to take that divergence. You take the x1 derivative of the first slot, the x2 derivative of the second slot, and the xn derivatives of the last slot. That is precisely the Laplacian. So woo! In the end, our Laplacian term appears, and you get that our phi prime of r, which again was the integral over that surface thing of divergence of du ds of y over some constant. That's the same thing as, actual ball. The integral over the actual ball of Laplacian of u dy over some constant. And now let's use the fact that the Laplacian is 0, because this is 0. We indeed get that the derivative of phi is 0. And so phi is constant. Ta-da! So it's very neat, at least so far. What did we do? We had this weird expression that depended on r. We use a change of variable, so hard multivariable calculus. We differentiated that, and it turns out this precisely gives us a normal vector for which we can use the divergence theorem, and precisely our divergence is the Laplacian. So how cool is that? And now let me conclude. So what did we find? Phi of r is the average value over bxr of, again, u of y, ds of y. In other words, we found that this value is constant. Okay. So in other words, if you take a surface, a sphere of radius r, and you average u of y over it, this average doesn't depend on r. And lastly, all you have to do is you let r go to 0. And you find that this thing, well, because u is continuous, just assume u is continuous, as r goes to 0, so think of a very small radius, the value of u is very close to u of x. So in particular, the average value of u should be very close to u of x. In other words, as r goes to 0, this thing goes to u of x. And if you're not satisfied, feel free to use an epsilon delta argument by just writing this as the average value of bxr, if you'd like. Write this integral as the integral of u of y ds of y over n r to the n minus 1 alpha n, and compare it with u of x. And again, u of x doesn't depend on y, and in particular, this constant is just the average value of that constant. So you can also write it as the average value of u of x over that sphere. And if you'd like, then just, compare the difference of the two and show that it goes to 0 as r goes to 0. So that's another way of doing this, if you're not completely satisfied. But anyway, so phi goes to u of x. So in other words, this thing that doesn't depend on r at all is actually equal to u of x. Because the idea is, at u it has value u of x. So, and because it's constant, the phi of r is identically equal to u of x. And therefore, the average value of u over that sphere is equal to the value at the center of that sphere. Alright, so that proves one of the things. Let me show the other one, but don't worry, the other one is much easier now because there's a clever trick. So, second, let me now show that this thing, the average value of u over any ball equals to u of x. And for this, let me just start with the left-hand side. So the left-hand side is the integral over u over that ball divided by the area, or I guess the volume of that ball. And you don't really need to know much about the area of that ball because, except that maybe it factors like r to the n. So I've also done a video on the volume of the ball, and it turns out the volume of the ball is r to the n times the volume of the unit ball, which I write as alpha n. And you have this, u of y dy. And now comes a very, very neat trick. So, suppose again, this is the unit, the ball of radius r centered at x. What we do know is the value of u around spheres. So take, for example, a sphere of radius t and centered at x. So b of xt. And let's try to compare the value of u on that sphere with the value of u in general. So b of xt, u of t, ds of t. And this is what I'd like to call the onion formula, or the polar coordinates formula. Namely, if you think of the ball, bxr, is actually composed of many shells of spheres bxt. And in fact, if you sum up the values on those spheres, you actually get the integral over that ball. So it's a legitimate thing. It's called the co-area formula, or the polar coordinates formula, or the onion formula. And it says that the integral over a ball, if you want, bxr of a function, it's the same as the integral over spheres of that function. So f of y, ds of y, except you integrate t from 0 to r. You see, so t is our parameter here, and you let it go from 0 to the radius r. So it is true. And again, over alpha n, r to the n. That said, that's super useful because, as I said, we know the average value of u on those spheres. And for this, we have to use 1 again. So what does 1 say? 1 says that the average value of u on that sphere equals to u of x. So the value at the center of that sphere. But again, what is average value? That's the integral divided by the surface area of that sphere. I'd like to remind you the surface area of that sphere is just n alpha n t to the n minus 1. So the derivative of the volume of the ball, which tells us that this thing, the surface integral over that sphere, is just u of x n alpha n t to the n minus 1. So this whole thing, and I forgot you. First of all, you integrate this from 0 to r, my bad. and you integrate that with respect to t. So this whole thing here just becomes u of x n alpha n t to the n minus 1. So you took this complicated thing, turned it into a much simpler integral, in fact just a one-dimensional integral. And this in the end becomes, let me write this in a new thing just to be a bit clearer. So we found the average value of the over that ball of u of y dy. We now found this equals to the integral from 0 to r of u of x n alpha n t to the n minus 1 dt over alpha n r to the n. And this looks like a lot of gibberish, but notice most of the terms, they come out, in fact all the terms except t to the n minus 1, and so we get u of x alpha n integral from 0 to r n t to the n minus 1 dt over alpha n r to the n. The alphas, they just come out. And this integral is just a simple single variable integral. An antiderivative is t to the n, and you do it from 0 to r, so you're left with r to the n minus 0 to the n, which is r to the n. And so in the end, you have u of x, r to the n, divided by r to the n, and this cancels out, and you're left with u of x. So even the average value on that ball equals to u of x. How neat! And it's just based on this co-area formula, which tells you that the integral over the ball is just the integral over the sphere, except you integrate the radius from 0 to r. And I'm almost done. I just want to talk about one more property. Because I said, if u solves Laplace's equation, then the average value of u on any ball or any sphere is just equal to the value at the center of that sphere, or that ball. It turns out the converse is true as well, so let me cover that as well. So, in case you're still watching, I'm so proud of you, but it's one of my favorite theorems. So, namely converse. Suppose u, so if u, again, smooth enough, okay, satisfies that the average value over any sphere of u is the value of the center, so for all x and r, then in fact, so suppose again you have a function whose average value is the center, then it turns out the only function of that form has to satisfy Laplace's equation. Okay. And in fact, to prove this, we have to use just part of the first part of the proof. So suppose not. So proof. Suppose not. Then the Laplacian is 0 somewhere. So for some x, the Laplacian is non-zero. Otherwise, it would be 0 everywhere. And if it's non-zero, it's either positive or negative. So let's just assume it's positive. So without loss of generality, assume u of x. Laplacian of u of x is positive at 0. And now, assuming u is smooth enough, so assume u is C2, which means this function is continuous. Let me just draw a little picture. So we have the Laplacian of u, well, x is positive, and because this function is continuous, around x, it's also still positive. So if this is, a sphere of centered R, or ball of centered R, Laplacian of u is still positive. So Laplacian u is positive on bxr for some r. And now let's consider the function phi we had from before. So let phi be the average value over that sphere of u of y ds of y. And remember, by assumption, I said the average value of u on that ball equals to u of x. So the value of that center. And more importantly, because this u doesn't depend on r, this is independent of r. In particular, phi prime is 0. That said, remember what we calculated from before? At some point, we had the following. But again, phi prime is 0. But we also calculated phi prime in terms of the Laplacian. So I think it was n alpha n r to the n minus 1 integral over that ball of Laplacian of u of y dy. Again, that was from the divergence theorem. But remember what we said? We said that on that ball, for r small enough, the Laplacian is positive. So this whole integral is positive. And then what you get is that 0 is greater than 0, and that's a contradiction. A contradiction with what? A contradiction with the fact that u is non-zero somewhere, so u has to be contradiction with the fact that the Laplacian is non-zero at somewhere, and so Laplacian has to be identically equal to 0. So it's very cool. We've actually characterized, all the functions which equal to their average values. So it's kind of neat. It's like a settled problem. All right, so I hope you liked this cool Laplace's adventure. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.